precision. That's a big term. Okay. Precision is the difference between the average value and the reading expressed as a percentage of the value. Okay. And it tells the ability of the instrument to reproduce its own reading again and again. Along with precision, there are 4 terms connected to it: repeatability, reproducibility, sensitivity, consistency, and what is the other term? Consistency and stability. Yeah, stability. So those 4 terms we have discussed. Repeatability and reproducibility for short-term duration, consistency and stability for long-term term. Okay, associated with long-term. And repeatability is the standard testing conditions. Reproducibility is with varying test conditions. Similarly, stability and consistency. Stability is for the constant test conditions. Consistency is for varying test conditions. So those 4 terms we discussed. And then drift is what is meant by drift. The deviation from the actual value. And normally the instruments may have 0 drift, and that is the difference between the when no input is given. If instrument shows some reading, that's called 0 drift. I think last class we somewhere stopped here. Any questions on whatever we discussed so far? Anything you want to ask me? Sensitivity is another important term. Sensitivity tells the incremental change in output signal to the incremental change in input signal. It is a ratio of incremental change in output signal divided by incremental change in input signal. So sensitivity is defined like this. This is not the final definition. This is a kind of initial definition. You know, we just say change in output signal divided by change in input signal. Okay. And change in output signal divided by change in input signal. It tells dy by dx. If x is in the input in the x-axis, output in the y-axis, then it becomes dy by dx. What is meant by dy by dx? It's a term familiar to you. Yeah, slope of the curve, slope of the line, whatever it is. Okay. When it is a straight line, you can say change in output signal divided by change in input signal. When it is a curve, the relationship between input and output is not linear. When it is non-linear, then you use the additional term incremental change in output signal divided by incremental change in input signal when delta x tends to 0. While delta x tends to 0, why we say delta x tends to 0? If it is a straight line, the dy by dx is going to be constant. Whereas, if it is going to be a curve, every point the slope of the curve will change. So you should exactly say at what point you compute this slope. If you compute slope here, it will be different than here, than here, than here. So for a non-linear instruments, where what is meant by non-linear instruments? If the input and output relationship within the instrument is not a straight line, but it is a curve, then this definition will not hold good because the slope is not a single value. It keep on changing at every point. So the perfect definition will be this: differential change in output divided by differential change in dy by dx, and delta x tends to 0. What is the meaning of delta x tends to 0? Yeah, delta x is basically a line. Delta x tends to 0 is actually a line length becoming 0. It's actually a point. It's actually a point. So delta x tends to 0, meaning it's It's not 0 but tending to 0. But there is a length, isn't it? It's only tending to 0. It's not exactly 0. It's not delta x equal to 0. It is delta x tending to 0. That means it is going closer and closer to 0. That's the perfect definition of point, isn't it? A line with almost 0 length is a point. So this is actually meaning a point at a given point. So at a given point, the sensitivity you compute as dy by dx. What is dy? What is dx? That becomes sensitive. Okay. You give 1 psi pressure in the quadrant tube. You want to know how much there is a deflection. If you give 1 psi and there is 5-degree shift in an angular term, 5-degree shift, and you give 1 psi pressure, there is 2-degree shift, which is having more sensitivity. 5-degree shift or 2-degree shift?
5 degree.
5-degree shift. Why? The change in now it is atmospheric pressure. You give 1 psi extra. That means the delta P, the change in input signal is 1 psi. Both the cases. There, first case, the delta Y change in output is 5 degrees. In second case, it is 2 degrees. So 5 divided by 1 is 5. 2 divided by 1 is 2. So 5 is having higher sensitivity. Okay. Would you like to have high sensitive instrument or low sensitive instruments? Huh? What is the requirement?
If we measure values like 0 to 1, we have to take the higher sensitivity one, and if we need like 0 to 10 or something, we need to take a low sensitivity.
Give me an example where you need a differential.
Voltmeters, ammeters, where sometimes we need from 0 to 1 ammeter, like ampere. So we will have a higher sensitivity one.
Okay.
And for 0 to 100 or something, we will have a lower sensitivity.
It is not we wanted it. There is already a relationship which is non-linear. You have no other go. You don't have linear instrument. So you use non-linear instrument. But given a choice, okay, no, somebody is already given in marriage to you. You have to live with her. There is no other go for you. But if two girls are shown and then say which one you want, you have a choice, isn't it? Now I am asking about the second case. You have a choice. Do you want linear instrument? Sensitive instrument or less sensitive instrument? Which one will be best for measurement? Huh? High sensitive, low sensitive, or medium sensitive? Huh? Which one will be useful for the right measurement? High sensitive, not medium sensitive and low sensitive. Why high sensitive? Accurate reading. Sensitivity guarantees accuracy. We can see the better output. Is that an advantage? Is that an advantage? What way it is an advantage? Sorry? It? That's what I'm asking. Even she was telling the same thing. She says you will get an accurate value. What way it guarantees accuracy or precision? Sorry? Resolution is connected to sensitivity. Is it? Sure. You can have maybe more graduation in between because for small input there is a bigger deflection. Now, what is the advantage of having higher sensitivity? What is the advantage of having higher sensitivity? No idea. Very good. See, normally in electronic instruments where the signal is taken from the sensor, if sensor gives higher output voltage for the given physical input, it is easy to do signal processing. It is easy to do signal processing. Suppose you take a thermocouple, okay, 10-degree difference, if it gives 5 millivolts change, or maybe 1 degree difference, it gives 0.2 millivolts change. Okay, that 0.2 volt is very small volt for us to measure, amplify, and do signal processing. You have to do calibration and display whatever is the temperature accordingly. For the same 10-degree difference, if the thermocouple gives instead of 0.2 millivolt, if it gives 2 millivolts, 10 times higher, it is easy for us to measure 10 millivolt than 0.2 millivolt very accurately and do rest of the signal processing and then do. Especially when we have circuits like amplifier, filter, every stuff has some minimum voltage that the input signal should have, so that it doesn't get lost in the process of signal processing. You have a machine, for example, the rice grinding machine or flour grinding machine. You cannot put the 4 grains on top of it and then try to get a flour out of it, isn't it? The dough doesn't come out of it. Okay, it does just go inside and it is got stuck inside itself. You should put minimum half kg, 1 kg, something, so that some flour will come out of the grinding machine, isn't it? Same way, these electronic circuits also, there is something called loading. In the maybe end of this class, we will talk about that. The instrument itself will take, the amplifier itself will swallow some amount of energy sometimes. Not all the circuits, certain circuits swallow some amount of energy in the process of signal processing. Okay. So if the incoming signal is too weak, that get lost in the amplifying process or in the filtering process or any signal processing process. Finally, what comes out as is zero. There is no output at all. If it is little more than that zero threshold value, you will get some voltage, but then it is not the perfectly signal processed value that we get. For signal processing, the input voltage itself should have certain minimal strength, minimal current and minimal voltage, so that the signal processing is performed easily and the distortion is not there. What you expect, that output you will get. Okay. For this, the sensor itself gives higher output value for the smaller values. The instrument will be capable of measuring smaller values, yet it gives enough strength signal so that can be processed and displayed to you so that you can take the reading. So sensitivity is good in most of the sensors, wherever, of course, electronics, voltage signal is involved. You convert it into an electrical signal and process the electrical signal. How about mechanical signal? As somebody said, sensitivity does not guarantee accuracy, does not guarantee precision. It simply gives a bigger output. Okay, I am telling somebody to write an answer for a question. Somebody writes in small letters, somebody writes in big letter. Somebody who writes in big letter, there is no guarantee that answer will be right. There is no guarantee that answer will be right. Sensitivity is exactly that, the size of the letters that you write on the board. But correctness doesn't depend upon the size of the letters. It is easy for you to correct. Oh man, you easily read it and then say, no, this is not correct, this is correct. So it's easy for us to take reading in case of sensitivity is high. So it does not assure the accuracy. Also, the precision is also not attached to the sensitivity. Sensitivity tells there is a bigger output for a smaller input given to the instrument. That is all it talks about. Okay. So sensitivity is defined as the ratio of change in output signal divided by change in input signal. I said the precise definition is incremental change in output signal divided by incremental change in input signal. Okay. For digital instruments, normally we don't talk about sensitivity. We don't say it is not applicable for digital instruments. Sensitivity. Why? the slope of the curve will be like this. You give an input signal, either it will give 1, this is 1 or 0. 1, 0, whatever. Or you keep increasing the input. Up to this doesn't change. The output doesn't change. Here it is 1, here it is 0, here it is 1, here it is 0. So the input signal is mostly analog. For example, you have a digital pressure gauge or digital temperature sensor. You have a hot bath where the temperature keep on increasing. The increase in temperature is not jumping 1 degree, 2 degree, 3 degree, it is not jumping. It gradually increases from whatever is the current temperature to a higher temperature. Continuously it varies. Okay? Similarly, if you have a pressure gauge and then a compressor is compressing, air is being pumped, let's assume continuously. Compressor normally it's intermittent process. Let's assume continuously the pressurized air is coming and the pressure is increasing, keep on increasing. Then you put a digital sensor there. When you see 1 bar pressure, maybe 1.1 bar pressure, 1.2 bar pressure, 1.3 bar, 1.4 bar. Between 1.1 bar and 1.2 bar, there are pressures available. 1.1 bar in case of pressure measurement, 1.2 bar. Let us say our instrument is capable of measuring 0.1 only. The second degree, the second decimal, it will not be able to measure. The capacity of our instrument is only that. Between this measurement and this measurement, the pressure would have increased like this, maybe 1.11, then 1.12, then 1.14, 13, 14, 15. All this, our instrument will not be able to measure. Only when it reaches 1.2, it increments to the next value. Then it keeps mum till it becomes 1.3. The moment it reaches 1.3, it shows 1.3. So, digital instruments behave like this. Because the slope of this kind of curve is either 0 or the full value. It just jumps from two value, swapping here and there. We normally don't attach a term called sensitivity for digital instruments. So sensitivity we attach or describe the term we will use to describe the analog instruments. You know what is the difference between analog instrument and digital instrument? Anybody do not know what is meant by analog instrument and digital instrument? All of you know? For both, there is no response between what do I understand. I am raising my hand. How many of you know what is the difference between analog instrument and digital instruments? Okay. How many of you do not know the difference between analog instrument and digital instrument? Yeah, you should tell, then only we will describe. Okay. In the laboratory, you might have seen a board and tube pressure gauge. Yes. Once you apply pressure, the needle keep on moving proportional to the pressure. Once you release the pressure, it comes back to 0. You also have seen another pressure gauge where there is an electronic sensor attached to the bottom of the tank, and then wires come, there is a Wheatstone bridge, and then some signal processing. Finally, PSI is shown in the digital form. The gauge, the board and tube pressure gauge, is an analog instrument because proportional to the pressure that you give, it moves. You may not be able to read because your scale may be having some limitation, but whatever is the pressure that you give, proportional to that, there is a proportional movement of needle. It's not jumping from 1 to 2, 3 to 4, 3 to 4 to 5. It doesn't jump. It moves gradually. That means it has infinite resolution. It can take any position in the scale and in the graduated scale. It is only your inability to take the corresponding reading. The gauge has infinite resolution. It can take any position on the gauge. Such measurements device are called analog instruments. Okay, it doesn't have any inability to show. Of course, the inability comes because the scale that we have drawn, we have calibrated, will have 1 bar, 1.5 bar, 2 bar, 2.5 bar, like that. Between 1 bar and 1.5 bar, we may not be able to read because there is no space to draw the lines, so we may not be able to read exactly. But needle will show all the pressures. Okay. In the scale, that is analog instrument. Digital instrument is the one with the electronic sensor, signal processing, finally a digital display. So many PSI shows. There, I think in the lab we have instruments like this. It will show a decimal point and then 1 digit. Second digit it won't show. Second digit it won't show. Okay. So actually it reads in PSI in our lab, pounds per square inch. So that will jump from 1.1. The next reading it is capable of showing is 1.2. So either this or that, then 1.3, 1.4. So it jumps. Okay. So that kind of instruments are called digital instruments. It is incapable of showing any reading between 1.1 bar and 1.2 bar. 1.2 bar and 1.3 bar. Anything in between, it cannot show. So it has predefined definite states. That's why it is called digital instruments. Okay. If there are only 2 states, either on or high, they are called binary instruments. Either on or off, yes or no, binary instrument. This is digital instrument. It has multiple points, predefined multiple points. After 1.1 it will show only 1.2. After 1.2 it will show only 1.3 bars. Okay. In pressure measurement. In temperature measurement it will be degrees Celsius. Clear? Fine. So sensitivity of digital instrument is actually not applicable. We don't say. Another important aspect. What will be the what is the definition of sensitivity? Incremental change in output signal divided by incremental change in input signal. Then what will be the unit of sensitivity? Huh? No unit. Very good. That is how even I thought. But you take thermometer. You take thermometer. What is the input? We are giving temperature as the input, isn't it? We are giving heat input, isn't it? Heat input. We would like to know what is the temperature. So it's a temperature in degrees Celsius is the input. What is the output? Proportional to the temperature, the liquid level increases in the thermometer. So what is the output? Output is measured in terms of some height units, isn't it? Maybe mm or something like that. Okay. Of course, there is a graduated scale. We take directly reading from thermometer in terms of temperature, but normally it is a displacement of the liquid column, and that's actually length units. That's in terms of meters, millimeter, meter, centimeter, some unit of length, meter. So output is measured in different units, input is measured in different units. Then finally, will the instrument will have the parameter will have some unit or not? It will have some unit. So you will see that in terms of thermometer, it is output unit divided by input unit. Output is measured in mm, input is measured in degrees Celsius. So the dimension of sensitivity of that particular instrument is mm per degree Celsius. Similarly, if there is a pressure gauge and that the output will be mm per pascal. So much mm displacement for 1 pascal pressure, something like that. So it is the unit of output parameter divided by unit of input parameter will give you the unit of sensitivity. Initially, even I thought both are same, output by input, output signal by input signal, so it's all same, so there is no unit. Because the units are different, you cannot ignore. Okay? Fine. Linearity is another term which I could have discussed along with accuracy. Linearity is another term. Exactly same as accuracy. There is nothing different. There is nothing different. See, linearity is plus or minus, measured value, true value, distance deflection, max, link, everything is same. The only difference is, for linear instruments, we use the term called linearity. For non-linear instruments, we use the term called accuracy. Okay, so you should know when we use linearity, when we use accuracy. Accuracy and linearity is all one and the same. One and the same. Meaning wise, formula wise, definition wise, everything is same. Sir, then what is the difference? This linearity we use for linear instruments. Accuracy is a term that we generally use for non-linear instruments. You know what is the difference between linear instruments and non-linear instruments? Linear instrument, non-linear instrument. We take thermometer, same example. We have been discussing, isn't it? Input is temperature, output is the displacement. If temperature in degrees Celsius and the displacement in the column of inside the thermometer, if this varies with respect to this linearly, let's take this is input, this is output. If this relationship is linear, input in thermometer is temperature in degrees Celsius, output is the displacement of the column, isn't it? Column of liquid that is measured in mm. That is measured in mm. If this input and this output for thermometer is linear, if I give 1 degree Celsius, 1 mm, need not be 1 to 1. 1 degree Celsius, 1.5 mm the liquid moves. 2 degrees Celsius, 3 mm moves. 4 degrees Celsius, 4 into 1.5, 3 mm moves. Like that, if the relationship between the temperature and the displacement is linear, then you call that instrument as a linear instrument. When you call as non-linear, let's say up to 100 degrees Celsius, some linear. After that, it turns like this. After that, turns like this. Most of the instrument is like that. Up to certain range, there is a linearity. Then it starts behaving in a non-linear manner beyond certain place. So up to this, if you use the instrument, it is linear instrument. You go beyond that and then say, here 1 degree Celsius means here 1.5 mm. Okay. Whereas in this region, 1 degree Celsius, if you increase, here it is supposed to go like this, but then it is here the corresponding difference from here to here will be maybe instead of 1.5, maybe 1.2 mm. Here maybe 1.1 mm. Here maybe 1 mm itself. Then it is a negative slope. Okay. So here it is perfectly linear, 1 to 1 up to here, and beyond which it is not linear. If you use the instrument only within the linear range, you call that instrument as linear instrument. If you go beyond and then start using here also, maybe 150 degrees Celsius you define as the range and use, but your instrument is calibrated. But non-linearly you have calibrated your instrument. Whatever is the temperature, your instrument will show the correct reading. But internally, the relationship is not linear. There is a non-linear relationship between input and output. So, if the instrument behavior is not always linear, then it becomes non-linear instrument. We are talking about the instrument which is for smaller values it is linear, that means long, big readings. After that, small readings are there. Some of the analog meters also you can see. There is a non-linear scale that you can graduate. It is graduated that you will be able to see. Initially, for smaller readings, you will see the graduation is bigger. As you go higher values, the graduation will become small. But still, the instrument will measure correctly. That's because there is a non-linear instrument. It is calibrated for non-linearity. So, you will be able to measure. You should not sleep. You should be able to measure the parameters correctly, but in a non-linear fashion. Okay. So linear instruments means input and output, the characteristics are directly related. There is a linear relationship exists between input and output. For non-linear instruments, that doesn't exist. There is a non-linear relationship. Alright? You just came out of the bed or feeling sleepy? The problem is this, since it is getting recorded, we cannot have much interaction in between. So continuously somebody is speaking for 40 minutes, 50 minutes, you feel little sleepy. La? What is that? Yesterday you traveled night? No. Fine. So this is linear. Readability is a very easy term. It is the easiness with which one can take reading from the instrument. It is the easiness with which one can take reading from the instrument. You have digital instrument. For example, vernier caliper. If you have used vernier caliper, you move like this and then take reading. Earlier, there will be a main scale, there is a vernier scale, you have to take this reading, that reading, and least count, you have to compute, take all that as a measuring instrument. Was that easy? Or now, same vernier caliper comes with a digital readout. You just move, the reading is shown 3.53 mm. 53 means 53 it shows. You don't have to compute anything. So which has better readability? The electronic output readout is better readability. So readability is the easiness with which you will be able to take reading. Why readability we learn? Because there are industrial regulations, especially when you have analog meters. In industrial atmosphere, if a person is using, his duty is to watch a gauge quite often, his eye will be strained very much. So there is an industrial regulation. If a meter is supposed to be qualified for an industrial gauge, and if that meter will be used in a shift where people often take reading in an 8-hour shift, then the instrument should have 1.5 mm per graduation. That means the graduation means, if there is a scale, let's take one first reading maybe 0 psi, next reading maybe 0.1 psi or whatever, 0.1 reading. The physical gap between first graduation and the second graduation should be 1.5 mm. This is an industrial regulation. 2 consecutive regulation. If it is less than 1.5 mm, the operator will find it difficult to read whether it is 1.1 or 1 or no, very difficult to read. So his eyes will be strained very much. In order to safeguard the operators, to qualify the gauge as an industrial gauge. That's industrial regulation. That term is readability. If it is below 1.5, we say it is poor readability, not qualified for industrial gauge. If it is 1.5 and above readability, 1.5 mm per division, then it is an industrial gauge. It can be any bigger than that. Minimum 1.5 mm. Hysteresis. Hysteresis is there is a forward loading and reverse loading. What is meant by forward loading and reverse loading? Not always something to do with loading, but mechanically people give an example. Mechanically people give an example, it is easy to understand. You take a cantilever beam, hang a weight band, keep adding the weight, 100 grams, 200 grams, 300 grams, up to 1 kilogram. There is a deflection. There is a deflection. Put a strain gauge, you will be able to measure what is the deflection, what is the strain. And keep removing 100 grams per time. 90 grams, 80 grams, blah blah blah, like that. Then how much? 0 gram it has reached. No more strain. If you, whatever you kept loading, that is forward loading, forward loop, forward path. What you kept reducing the weight, that's a reverse path. In that process, we expect, initially the cantilever beam did not have any deflection, 0 deflection. My strain gauge showed 0 reading. That means indicating there is no deflection. Now I have bent and then brought back to 0, again no weight. But instrument is not showing 0. Instrument is not showing 0. It is supposed to show 0, but it is not showing 0. This is because of hysteresis. This is because of hysteresis. It is the difference between the forward path and the reverse path. Difference between the forward path and the reverse path. I expect the instrument to show 0. This is the, I mean, maybe after some time, maybe after half an hour, after 1 hour, it may regain its position, maybe it's showing 0. But once I removed all the weights, immediately I expect the instrument to show 0, but the instrument is not showing 0. This is the starting point. There is no deflection, but after that I start loading, I get 1 kilogram. Then reverse path is this. I reduce 90 grams, 80 grams, 50 grams, 40 grams. Here I remove all the weights. I expect the reading to be 0, but some difference is there. Some reading is there. So this height, this much output is given by the instrument even when there is no input. That difference is called hysteresis. That is the, you take an electromagnet, take an iron core, you put a coil over it, you supply small amount of current. To that amount of current, it becomes an electromagnet. That iron piece will become electromagnet. You increase the amount of current that's passing through that, it becomes stronger and stronger magnet. Magnetic field strength increases. Then you keep reducing it, then magnetic strength comes down. You cut off the circuit. That means no current, nothing, no more coil, remove the coil, everything. We take the iron piece, we expect this to be ideally a normal iron piece. But there will be some magnetic field, magnetic property still attached to that material. That's called stray magnetic field. Stray magnetic field. Some residual magnetic field will be there. Here also it is residual stress. It has gone through some stressing process. Stresses are relieved completely, but still I am under stress. So that's called residual stress. Okay. We also have hysteresis. You know, let's say as per Indian astrology, I don't know, some of you, your belief system may not support astrology, but as per Indian astrology, 7.5 years is Shani Bhagavan's tough time. Okay, he will give lot of trouble to you in life. After 7.5 years, actually Shani Bhagavan would have stopped giving troubles, but you continue to be sad and demotivated, and for some more time. That is not because of Shani Bhagavan. That's because your own hysteresis. You don't have agility to realize that and come out of that problem. Okay. So that kind of behavior is there anywhere. Every instrument has this. Some instrument has little hysteresis. Some instrument has higher hysteresis. We wanted to quantify and tell. We do not want hysteresis at all. Hysteresis is a kind of error. We do not want any hysteresis. Ideally, we should not have hysteresis. Ideally, we should not have hysteresis. Okay. So this is not only with respect to 0, also with respect to negative loading. Okay. So it's not at any given point of time, it is the difference, maximum difference between these two paths, a forward path and a reverse path. It's not from 0 to there. If the cycle goes on the negative side also, then the difference between these two is called hysteresis. Earlier I discussed only the positive cycle and said from 0 to the top, this difference is hysteresis. The global definition, a better definition is, if loading is possible, let's say cantilever beam is 100 gram to 100 gram up to 1 kg, then it is bent normal. Then it is bent in the reverse direction. You pull 100 gram to 100 gram up to 1 kilogram pulling, then you brought it back to normal. That means a positive loading and a negative loading. Whatever, two types of loading. Then you have a positive path, and a negative path. There are two paths. The difference between the two paths is actually the hysteresis. At any given point of time, you want to know what is the hysteresis at the 0 loading, the difference between this. At this loading, it's this. At this point, you want to compute, at that particular height, what is the hysteresis. So, the hysteresis go on, at every point the hysteresis will be different. You should compute what is the maximum hysteresis and indicate that as the hysteresis of that particular instrument. What is the maximum amount of difference between the forward path and reverse path? For that instrument, you compute and refer, that is the hysteresis of the instrument. So your formula would be percentage of hysteresis error is upscale reading minus downscale reading at maximum. It's not at x maximum, at maximum. That means whichever is the difference maximum difference between these two upscale reading and downscale reading. Take the maximum difference into 100 divided by full scale deflection is the formula for hysteresis here. Anybody do not understand what is meant by upscale reading, what is meant by downscale reading? Because there will be a problem in the examination. Theory I am explaining. Only if you understand theory you can solve problem. Problem I am not working out. If you understand the theory clearly, you can solve the problem. It's only common sense. Do you understand what is meant by upscale reading, what is meant by downscale reading? Anybody do not understand, please raise your hand. Otherwise you cannot solve the problem. Yeah. I'm having a cantilever beam. I put 100 grams upscale reading. 200 grams, 300 grams, the shaft keep on bending downwards. The corresponding deflection will be there. 1 mm deflection, 2 mm deflection, or something like that. Some deflection will be there. The entire exercise I have done is forward path. Okay. Then I kept on reducing. That is reverse path. And then minus. I put a spring balance and pull 100 gram pull, 200 gram pull, 300 gram pull, so that I am pulling the cantilever beam upward. Take the deflection, how much mm it is deflecting for 100 gram of pull, 200 gram of pull and things like that. And that also I take the reading. Okay, that's a complete reverse path going up to 1 kg, minus 1 kg on the outside. Again coming from there, minus 90, minus 80, minus 50, minus 40, minus 10, 0. Then it has reached. That is forward path. Going again 10, 20, 30, 100 gram, 200 gram up to 1 kg. From minus 1 kg to plus 1 kg, the path I travel is forward path. From plus 1 kg to minus 1 kg, that I travel is reverse path. Corresponding deflection also I should note it. This is the forward path and reverse path. At this point of time, some place there will be more deflection, some place there will be less deflection than what is expected. I say 100 gram 1 mm. 200 gram it should be 2 mm, maybe 2.2 mm, maybe 3.1 mm, something like that. There will be difference. The forward path and reverse path, you find out the difference at this is one forward path, this is the reverse path. At any given point of time, where is the maximum difference between these two paths you have to compute into 100 divided by full scale deflection. The instrument's full scale deflection is to be given by the examiner. If you are in industry, you have to look, take the meter, see what is the maximum reading that instrument can measure. That's the full scale deflection. Alright? So you will be able to use this formula in the exams and do problems by yourself. If readings are given to you, will you be able to compute hysteresis by yourself? Yes? Good. So we stop here and then we can.